In the world of computers, the CPU and GPU are the unsung heroes powering everything from simple calculations to complex simulations. These tiny chips, often hidden within our devices, are the driving force behind every click, every keystroke, and every pixel displayed on our screens. They are the brains and the brawn of our digital lives, working tirelessly to execute instructions and render graphics with stunning fidelity. The CPU, or Central Processing Unit, is often referred to as the brain of the computer. It handles a wide range of general-purpose tasks, such as running operating systems, executing applications, and managing data. From the moment you turn on your computer to the time you shut it down, the CPU is constantly at work orchestrating the intricate dance of data processing that makes modern computing possible. On the other hand, the GPU, or Graphics Processing Unit, is the brawn behind visually demanding tasks. Originally designed for rendering images, videos, and 3D graphics, GPUs have evolved into powerful parallel processing units capable of accelerating a wide range of computationally intensive tasks. From gaming and video editing to scientific simulations and machine learning, GPUs have become indispensable tools in various fields. This essay will delve into the inner workings of CPUs and GPUs, comparing their architectures, processing techniques, strengths and weaknesses. We will explore the fundamental differences between these two processing powerhouses and understand why they are both essential for modern computing. The CPU is a marvel of modern engineering, packing billions of transistors onto a tiny silicon chip. Its architecture is optimized for sequential processing, allowing it to execute instructions one after another with remarkable speed and precision. This sequential processing power is crucial for handling the vast array of tasks that a computer performs daily. At the heart of the CPU lies the Arithmetic Logic Unit, ALU, responsible for performing arithmetic and logical operations on data. Whether it's adding numbers, comparing values, or performing bitwise operations, the ALU is the workhorse of the CPU, tirelessly crunching numbers and manipulating data according to the instructions it receives. Working in tandem with the ALU is the Control Unit, CU, which fetches instructions from memory, decodes them, and directs the ALU to execute the corresponding operations. The CU acts as the conductor of the CPU orchestra, ensuring that instructions are executed in the correct order and that data flows smoothly between different components. The CPU also includes a hierarchy of caches, small, high-speed memory units that store frequently accessed data and instructions. Caches act as intermediaries between the CPU and the main memory, reducing the time it takes to retrieve data and improving overall system performance. In contrast to the CPU's focus on sequential processing, the GPU is designed for massive parallelism. It achieves this through its unique architecture, featuring thousands of smaller, simpler processing units called cores. These cores work in unison, processing vast amounts of data simultaneously, making GPUs exceptionally well suited for tasks that can be broken down into smaller, independent parts. Unlike CPUs, which have a limited number of cores optimized for general-purpose tasks, GPUs boast a massive number of cores, each specialized for handling specific tasks related to graphics processing. This specialization allows GPUs to excel at performing repetitive calculations on large datasets, such as those involved in rendering images, videos, and 3D graphics. GPUs also have dedicated memory units, typically referred to as video RAM or VRAM. This high-bandwidth memory is specifically designed to handle the massive data throughput required for graphics processing. The close proximity of the processing cores to the VRAM further enhances the GPU's performance by reducing data transfer times. While initially designed for graphics rendering, the inherent parallelism of GPUs has led to their adoption in a wide range of non-graphical applications. From scientific simulations and machine learning to data mining and cryptography, GPUs are now used to accelerate computationally intensive tasks across various fields. The fundamental difference between CPUs and GPUs lies in their architectural philosophies and processing approaches. CPUs, with their limited number of powerful cores, excel at handling complex tasks that require sequential processing and decision-making. They are the masters of handling a wide range of tasks with high accuracy and efficiency. GPUs, on the other hand, are designed for brute force parallelism. Their massive number of specialized cores allows them to perform the same operation on multiple data points simultaneously, making them ideal for tasks that can be broken down into smaller, independent units of work. Imagine a CPU as a skilled chef who can prepare a complex dish with intricate steps and precise timing. In contrast, a GPU is like a team of cooks working in parallel, each specializing in a specific task, such as chopping vegetables, preparing sauces, or grilling meat. Both approaches have their strengths and weaknesses. CPUs are versatile and efficient for general-purpose tasks, while GPUs are powerhouses for parallel processing. Understanding these differences is crucial for choosing the right tool for the job. Section 5. CPU strengths. The master of one CPUs excel at tasks that require complex logic, branching, and decision-making. Their architecture allows them to handle instructions with multiple dependencies, making them ideal for tasks such as running operating systems, executing applications, and managing databases. CPUs are also highly optimized for single-threaded performance, meaning they can execute a single stream of instructions with remarkable speed and efficiency. This makes them well-suited for tasks that cannot be easily parallelized, such as text editing, web browsing, and running office productivity software. Furthermore, CPUs typically have lower latency than GPUs, meaning they can respond to requests and complete tasks with minimal delay. This low latency is crucial for real-time applications, such as gaming, video conferencing, and financial trading. In essence, CPUs are the versatile all-rounders of the computing world, capable of handling a wide range of tasks with high accuracy and efficiency. Section 6. GPU strengths, the parallel processing powerhouse. GPUs shine when it comes to tasks that can be massively parallelized, such as image and video processing, scientific simulations, and machine learning. Their ability to perform the same operation on multiple data points simultaneously makes them significantly faster than CPUs for these types of tasks. The massive number of cores in a GPU allows it to handle thousands of threads concurrently, making it ideal for tasks that involve processing large datasets, such as rendering complex three-dimensional scenes, encoding and decoding videos, or training machine learning models. GPUs also excel at matrix operations, which are fundamental to many scientific computing, machine learning, and artificial intelligence applications. Their specialized hardware and parallel processing capabilities make them significantly faster than CPUs for these types of calculations. In short, GPUs are the heavy lifters of the computing world, capable of processing vast amounts of data in parallel and accelerating computationally intensive tasks. Section 7. When to use what? Choosing the right tool for the job. Choosing between a CPU and a GPU depends on the specific task at hand. For general-purpose computing tasks such as web browsing, word processing, and running office applications, a CPU is usually sufficient. For tasks that involve heavy graphics processing, such as gaming, video editing, and three-dimensional modeling, a dedicated GPU is essential for smooth performance and high-quality visuals. In scientific computing, machine learning, and artificial intelligence, GPUs are often used to accelerate computationally intensive tasks, such as training deep learning models, running simulations, and analyzing large data sets. Ultimately, the best choice depends on the specific requirements of the task, including the computational complexity, the level of parallelism, and the desired performance. Section 8. The future of computing, a synergistic symphony. As technology advances, both CPUs and GPUs are constantly evolving, becoming more powerful, efficient, and specialized. The future of computing will likely involve a synergistic relationship between these two processing powerhouses, each playing to their strengths to deliver unprecedented performance and capabilities. Heterogeneous computing, which involves using both CPUs and GPUs in tandem to accelerate different parts of an application, is becoming increasingly prevalent. This approach allows developers to leverage the strengths of each processing unit, optimizing performance for a wide range of tasks. Moreover, the rise of artificial intelligence and machine learning is driving the development of specialized hardware, such as AI accelerators and neural processing units, which are designed to handle the unique computational demands of these emerging technologies. The future of computing is exciting, with CPUs and GPUs continuing to play pivotal roles alongside emerging technologies in shaping the technological landscape and driving innovation across various fields. Section 9. Conclusion. The enduring legacy of CPUs and GPUs. CPUs and GPUs are the unsung heroes of the digital age, powering everything from our smartphones and laptops to supercomputers and data centers. These tiny chips, with their distinct architectures and processing approaches, have revolutionized the way we live, work, and interact with the world. CPUs, with their sequential processing power and versatility, excel at handling complex instructions and managing the intricacies of operating systems and applications. GPUs, on the other hand, are parallel processing powerhouses capable of accelerating computationally intensive tasks and rendering stunning visuals. Understanding the strengths and weaknesses of CPUs and GPUs is essential for choosing the right tool for the job and harnessing the full potential of modern computing. As technology continues to advance, CPUs and GPUs will undoubtedly continue to evolve, becoming even more powerful, efficient, and specialized. Their enduring legacy will continue to shape the future of computing, driving innovation and transforming the technological landscape for generations to come.